All right, let's do this. This is time for our midterm exam review. Professor Darden here. This is my first shot on the live stream this semester. I'd like to jump in here and get us going for this midterm. So we'll start out talking about the structure of the exam, get into some pep talk stuff, then we'll talk about what's going to be the exam content. Here is the good news. The good news is that this is almost over. On the left, you see students sitting there tearing their hairs out just about how difficult this exam is going to be to take. On the right, getting no pity from you, I imagine, is the professors tearing their hair out about how hard this exam is going to be to give. But whether you live on the right side of the frame or the left side of the frame, doesn't matter. This is all going to be over soon. We'll get started tomorrow, and 140 minutes after you get started, it's all over with. The exam is tomorrow, March 10th. All of these times are in Ann Arbor frame. We're starting out with a 9 a.m. exam, a 3 p.m. exam, and then a 9 p.m. exam. And the hope there is that no matter where you are in the world, hopefully you could easily get to one of these exams, and probably without too much trouble you should be able to get to 2 of them, and then being able to choose the one that works the best for you. This is a 140-minute exam. This was originally a 90-minute exam, and without any format or content change, we ended up adding an additional 30 minutes just to make it even up with the final exam. Then once we went inside for the COVID here, we've given an additional 20 minutes for any kind of online tomfoolery that needs to happen, whether it's getting an exam downloaded and printed, if that's your style, or if anybody has any connection issues or spotty connection issues or general low speed. So you've got 140 minutes to get this done, and each one of these things starts at a given time, goes 140 minutes later. There are some of us that have extended time. If that's your case, you end up with just an additional hour for the 50%, because we're still thinking of that plus 20 minutes as a padding, not really as exam times there. So there's no need to really inform us which slot you're going to take. Just take it once and show up when you're ready to do that and get going. We will have staff on hand so that any questions that you ask can be answered during that time for clarification, as long as we're clarifying what the exam question was asking, not trying to give you information that you should have on your own. If you're taking an extended time exam, it still starts at one of those start times, 9 o'clock, 3 o'clock, 9 o'clock, and then goes for additional time after that. This is going to be a 2-part exam. There's multiple choice questions. That's going to be done via a Canvas quiz. And then there's going to be a couple of free response questions, which we will use Gradescope for. All of the question content is going to be in the Canvas quiz, however. That means that what to do for the free response questions on Gradescope has to be read on Canvas. So don't finish your multiple choice questions and then submit the exam planning to do your free response questions later, because that's where you can read them from. So use that, stay there. Then when you're done, submit the whole thing, but only after you've done the written questions on Gradescope. So that's what it says. Do not submit until you're done with both parts. There is an honor pledge that is a separate quiz. You'll have to fill that out the next day. We don't want anybody getting confused and submitting something that they shouldn't submit. So we have separated this by a day just to remove headaches. Problems for you and problems for me. During the exam, we're going to use Piazza for this communication. Normally, we have staff outside in the hall. Somebody runs outside, asks their question, and goes back in. Think of Piazza as substituting that functionality there. So during the exam, all posts on Piazza from our side will have turned on the setting that makes everything that gets posted private. So don't make your questions public. They're private on purpose so that you aren't sharing information unnecessarily across the other students in the course. So anybody who has a question during the exam, you post that on Piazza, and then we have staff sitting there waiting to answer those questions as soon as possible. It'll be some of our student staff as well as the majority of the faculty, depending on which slot you're in. One or all of us will be there to help answer those questions and manage anything that should go wrong there. So make sure that you post on Piazza if you have a question, and make sure that you don't mark that as public, because that'll really make people angry. And whatever you do, don't do a follow-up to a public post. Make sure that you stay within your own private post. Once you've got that question out there, it's going to take us some amount of time, even if that's 30 seconds, 1 minute. What you don't want to do is waste time during the exam. Post your question on Piazza, then go right back to working on something else on the exam, then check back at Piazza in a minute after the next question or whatnot, but try not to get yourself stuck waiting. You don't want to do any blocking during this exam. Nothing should stop your progress. Pause, fill out a question, move on. Make it happen like that. Set your browser to fill the screen too, because there's some strange formatting things that happen with Canvas. When people try to make their Canvas window too small, sometimes for some reason images that should be with questions just don't show up. So if you get to a question then you see something that feels like it's missing, try resizing your window. It's a really strange thing. Try to make that thing max is just as well there. That's a good way to do it. As far as the Piazza stuff goes, we will try to get that back to you as soon as possible. In terms of exam policies, you can use anything that we have given you. That means lecture PDFs, stuff from labs, stuff from the exams, although there's nothing directly from the projects, although there's nothing directly from the projects on the exam. Only things that we've talked about in lecture are really the material that you're responsible for examining with. During a normal semester, we allow you a cheat sheet. That would be one side of an 8.5 by 11 piece of paper. You've got a little bit more space on your desk now, but the policy is still the same. You should be using just this information here on a cheat sheet. And the reason why that's helpful is if you've focused and you've studied and you've notated the parts of the exam that you think you might need help with or aids, and you've brought them all along and you've prepped that and you put that on a cheat sheet, then you are prepared for an exam. If you're thinking, well, I've got access to all the slides, there's already been 500 slides this first half of the semester. If you're going to try to figure out something that's in a slide somewhere, there's not going to be enough time. If you run out of time, you're starting to lose points. We don't want you to lose points. So if you make a cheat sheet, it's really good because it focuses what you need to do, and you've made it very recently, especially if you write these things. It's really good. In the regular semester, we say you have to write this by hand. We don't want people copying and pasting things from slides or from the internet or wherever, because what happens when you do that is you've just got a bunch of copied and pasted material. Now, when you don't know something, you have to go do a search to figure out where that is. Whereas when you write that stuff by hand, you've planned out where it's going to fit, made it fit, you know exactly where it is. So when you need to get to that master theorem reference, you know, oh, it's right over here on this side of the sheet. You jump down there, you do what you need to do and fill it in. So it's a really good idea to do this. Another thing that is really helpful is as you are writing your cheat sheet by hand, your brain activates its motor cortex to make these loops and circles and lines. That's really helpful in terms of focusing your memory. It's adding an additional task to your brain, and studies have been used to show that this additional brain work while you're writing things down really helps with recall. They've shown that people sitting in meetings, even if they were just doodling on a notepad, they tend to recall what was said in the meeting better than people who are sitting there trying to focus on the speech alone. So try to write your cheat sheet out. I promise it's helpful. I learned this myself the hard way in college. I was taking notes, but I never really used them. And I would just go to class, take notes, bring them back, and they'd litter up my room a little bit. At one point, I just got tired of cleaning up notes and never using them, and I decided, well, I'll just stop taking them then. It's kind of a waste of time and got to deal with paper and all the other stuff. And then I started to do worse. When I started taking notes again, I started doing better, even though I wasn't still really studying off of them. It wasn't a skill that I really mastered, studying for my own notes. But while I was taking notes, I was doing better than when I wasn't taking notes. So that's why it's a great idea to do this. Make sure you write this stuff down by hand. It's very helpful. Of course, our final policy here on the slide, that the engineering honor code definitely applies. That means do your own work. Don't use anybody else's work, and let us know if you see somebody else doing otherwise. Excuse me. There's two sections on the exam. The first part is the multiple choice portion. This is 24 questions, numbers 1 through 24, each of them worth 2.5 points. Those of you with quick math skills will say that's 60 points on multiple choice questions. You would be correct. There's 4 to 5 possible answers per question. These are all A, B, C, D, or A, B, C, D, E, so don't think of any true-false questions. And you should be marking one answer for each question. There is one right answer for each one of these questions. So there's always one, never more, never fewer. So make sure that you answer all 24 questions, and this is a lot harder to have double bubbles now that we're doing this online thing. But when we're doing this on paper, we want to make sure you only bubble one. So one answer per question, no more, no less. The exam itself, of course, we talked about this being a Canvas quiz. There's multiple choice questions, just like you do for the lab stuff. So this isn't anything new. The written questions that we do are going to be just like in GradeScope. So there's nothing that should be new here. All of the things that we've done to practice for this exam during the semester, you are well versed in if you have kept up with what you're supposed to be doing. Another reminder here, do not submit the quiz until you're done with both parts, as then you won't be able to read about those last 2 questions on the free response. So mention here about the display issue, and this is some of the challenges of working with Canvas. The exam has a time limit, and in the way that Canvas does this, it takes the longest allowed time. So if we've got some accommodations that allow some students to take a 1.5 time exam or a 2 time exam, then Canvas isn't really flexible. It just says, oh, you need somebody to be able to take a 2 times exam. It will open that whole thing up for this 4 hours and 20 minutes. So if you don't have that extra time because you haven't submitted an SSD form, then you still are limited to the 1 hour and 40 minutes. It may say that you're starting late because you're not really getting 4+ hours. Don't worry about it. When you start, you've got 140 minutes. I wish this was better. This is kind of a Canvas thing. If you need to open up a watch or a timer on your desk to make sure that you feel comfortable about that, do something to make yourself feel comfortable so you're not worrying about what the time is. You can have some issues trying to figure out how much time is left on Canvas. That's something that's beyond our control. Apologies there. What should we be using to study? Of course, the practice exam. The practice exam is a version of an EECS 281 exam. It might be a little bit easier than the actual exam. It might be a little bit harder. Some of these things are for practice, so make sure that you use them as best you can. The answers for that will go live as soon as I finish this lecture here. So in about an hour and 15 minutes, you should be able to look at the practice exam answers on Canvas. If you haven't already done them, you should definitely be working on them soon. You can of course use the lecture slides and any of the recordings, either the live stream recordings or the pre-recorded recordings. All of those are good content. There's the in-class exercises, lab materials, projects. Even though we don't have project content on the exam, there was some things that you learned from the project. how to use a priority queue. There's definitely going to be talk about priority queues on this exam. So think about things like that, some of your syntaxes that you might have to use in terms of how do I use the STL? I'm going to have to write some STL style code on free response question number 1. That's problem 25. If you've got a study group, that's a great way to do this. One of the things that's really hard to do when you have material that you feel fairly comfortable with. Hopefully you all feel fairly comfortable with this. It's easy to figure out what you need to study when you don't understand something. You got to go study that. Or it's easy to say, well, I totally get that. I don't know now what I'm going to study. So a study group can be helpful for that as well. One of the things that I like to point out is every year we hire a bunch of new staff to help us with a course. And usually these are students who have just recently taken 281. This is about a third of the staff. And so I tell students getting ready to take this midterm, about a third of these questions were written by someone who has one more semester's experience in 281 than you do. That's to give you hope. That's to let you know, I can do this too. All I have to do is get past this midterm exam, and if I was going to be on staff next semester, I wouldn't have to learn anything more from the beginning of the semester to do it. So here you are at the point where you could be writing exam questions yourself, other than the fact that you're taking the exam. But that turns into a great way to study. Write an exam question. If you can write a multiple choice question that you think would reflect how would the teaching staff know that I understand this, that's the kind of thing that you should be worrying about. Say, I do understand this. I don't know how they're going to ask me a question to prove that I understand it. You say, well, let me take a multiple choice question and think about how might I do something with complexity, or how might I do something with strings and sequences. Every time you go through a lecture, you go back and watch lectures, or even as you're watching lectures now, try to jot down an exam question or two. Then if you've got a study group, swap your questions around. That's exactly how we make the exam. At the beginning of the semester, we pick one lecture for each staff member and say, hey, write some questions based on this lecture. And then we throw them into the pool, and those are your new exam questions. So you can do this too. It's not that difficult. Take some time, put some thought into it, and then if you've got some people to share this with, feel free to share it. The topics we're going to cover are everything that we've had in lecture so far, with a focus on, of course, complexity analysis, including recurrences. We'll be talking about the contiguous versus connected as we look at array or vector style containers versus linked list or pointer based things. Stacks and queues, of course. We've already had plenty of priority queue work, so hopefully you feel really comfortable with priority queues, but they'll still be on the exam. The binary heap will, of course, be on there. That's something that we definitely talked about in lecture. The pairing heap, not so much. Everybody's happy to not have pairing heap questions to deal with. So the pairing heap was not something we discussed in lecture, not going to be something that's on the exam. Heap sort, of course, will be because it uses the binary heap. So anything that's binary heap based could be used. Pairing heap, not so much. We'll talk about elementary and quick sort and merge sort, all of our sort stuff. There's the possibility of counting sort questions on there. But each one of these areas has a ratio. If you think about what's going on here, this is lecture 14. Lectures 1 through 13 actually had course content. So if there are 24 multiple choice questions and there's 13 content-based lectures, there's probably only 1 or 2 questions for each one of those lectures. So even if there's a situation where you feel like I didn't do well in this particular topic, or I don't really understand this well, I don't feel comfortable going into it, know that there's going to be 1 or 2 questions on that, and hopefully you can get lucky there or work your way away from your trouble areas. Or if you've got enough time, double down on studying in those sections and make sure that you've got it. Strings and sequences, our last lecture, that was given by Professor Noble here on the live stream a couple of days back. That one will be on the exam. There's 1 question there. So that's how the topics are going to go. What about these coding questions? We talked about the first 24 questions, 2.5 points each multiple choice. Now we've got some free response stuff here. There's 2 of those things. The first one is fairly straightforward. This is one that's going to use iterator mechanics. So you want to make sure you understand that. For example, review set intersection from the lectures. That's the kind of thing that we're talking about in terms of using iterators and making things happen. That's one question. It's going to be worth 16 points. The other one is going to be worth the other 24 points. So of those two free response questions, one is easier and one is harder. The thing about easy and hard questions like that is they're going to be scaled a bit in terms of how much code you have to write. So if you're wondering about how I might score some points, this is what you should be thinking. You're trying to think about how to score points. How am I going to score some points? It's harder to get partial credit on a small problem than it is to get partial credit on a big problem. Think about that. There's 24 points out there. If I can take a quarter of that, I can grab 6 good points, where if there's only 16 points in there and I can only get 20% of it, now I'm not looking at very many points at all. So be aware that as you plan how to get this done, there's some strategies that you can use to gain. When you're answering these coding questions, think about what we had to do to write a solution. Much like all of the other things that we do in 281, we're using about 150% budget. So we'll tell you how many lines your solution can take. Say it's 16 lines. Well, that means that we're giving you about an extra 50%. So what do we get that done in? We got that done in 10 or 11 lines. And so then we kind of bumped it up by 50% and said, you could do this in 16. If you see a 24 line budget, that means we probably got it done with a really average solution in about 16. If you're taking drastically more than that, then you're on the wrong track. Maybe you might want to tighten up your approach a bit. I've seen 30-line budget questions. Looks pretty large, but what that really means is we got a really decent solution, or 2 or 3 from the staff, done in 20 lines or fewer. So that's what you have to look forward to. If you need some sort of data structure, like you wanted to make a struct or something because you just couldn't figure out a way to solve this without having information passed around in a struct, then there's a good chance that we couldn't figure out how to do it either. So that budget assumes that you would be making one of those data structures. If you need a helper function, there's probably a solution that we have that has a helper function as well. So you should be able to do that. If you need to write the structure or the helper function, don't worry about where it goes. Just write it, get it on there. We'll be able to see what happens. The reaction normally when we're writing these things is, I want to make sure this compiles and runs. We're not compiling and running it for points. We may use the compiling and running to help us look towards a particular aspect of how we're going to grade it. But when we look at grading it, we're looking at code that we see there. This allows for some minor syntax errors, things that wouldn't compile. But if you show that you can do this problem solving aspect of the problem, even with some syntax irregularity, you have a great chance of still scoring really well on the exam. So don't get too bogged down in making sure that what you submit compiles. We don't use the autograder on GradeScope to give you points the way that we use the autograder on projects. So get the thing to work, and if you can, but if you can't, get the code on there, because we really want to see what you're thinking. We really want to see you solve this problem. All right? As we talk about how many lines this takes, this budget thing is pretty important here. Look at these two examples here. If x is greater than 0, set result equal to 0. Obviously, syntactically correct to do that first version, sort of an inline if you will. But the staff is still going to count that as 2 lines of code. That's a more reasonable way to write this, with this if x greater than 0, next line, set result equal to 0. That's how we think of 2 lines of code. Even if you try to write it in the first version as 1, we're still going to count it as 2. So make your code readable. There's nothing more important than readable code, especially on an exam. How about this one? If x is greater than 0, we're going to set result equal to 0, and then we're going to return result. And we've got a curly brace to close that up there, but we don't count curly brace only lines. This then is 3 lines of code. We've got if x is greater than 0, that's 1. The result equal to 0, that's 2. Return result, that's 3. The closing curly brace, not counted. We never count closing curly braces. How about this one? If x is greater than 0, set the result equal to 0, else set the result equal to x. Looks like 4 lines of code. Hopefully you got that. Great. But you could also use the ternary operator, which is legal. And a ternary operator is the one that uses 2 separators and 3 operands. In this case, x greater than 0 comparison is before the question mark. The 0 return value is after the question mark but before the colon, and then the x return value is after the colon. And what that does is it tries the test first. On success, it returns 0. On failure, it returns x. And you see here that if we assign the result of this, the return value of this expression to result, then we've got the exact same code in this one-liner as we've got in those 4 lines up above. So that's a thing that you can use. We don't write our code like that when we're setting a budget. So if we could have written it with a ternary operator, we would still write it with if-else as we calculated your coding budget. That says that you can use this, but you don't need to. If you don't understand the ternary operator or you're not comfortable with using it, don't worry about it. If you're trying to use a ternary operator to get yourself under budget, maybe you missed something and you're doing something that you don't need to do somewhere else. But be aware that the ternary operator can be a nifty little time saver because you write less, and also a space saver because it takes fewer lines. Same thing here if we're talking about putting a container of struct here. You see that we've got some struct that we had to declare here. Maybe this is from the word count demo. So we've got a string for the word and an int for the count. If you can put that in there, you can then make a vector of those things. So now I've got a container of structs, and that's a pretty nifty way to get something done if you need to on an exam there in a free response question. You see that there's a vector of word counts, and you can do some pushbacking there, and that one has allowed that to be created anonymously with that struct word count. In terms of what we can use from outside the libraries, the STL, each one of these coding questions is unique, and it will tell you exactly what you can and cannot do. It will tell you in terms of your time and memory budget, or your allowances for complexities right there, your time complexity, your memory complexity. Will also tell you what you can use from the STL, if anything. Some questions don't allow any STL, some questions do. If there are function headers that are required, those do not count to get you in terms of lines of code. The starter files that we give for these things have all of the headers that we used already included in them. If you feel you need to add more, you can, and it will not be counted against you. In terms of integers here, remember that loop variables, use the things that make sense. Most of the times, I like to use size t's in my loops. They almost always get me where I want to be. I'm normally counting from 0 up, and that's a great place for size t's, especially if I'm going to compare that to any container. Those are always going to be returned in terms of size t's. But don't worry about the conversion of those things. Don't worry about it. Write whatever makes you feel comfortable and gets it done for this exam. That's going to be helpful here because we are under a time crunch. There's always time to take code that works later and fix it in the real world. But remember, this is not the real world. This is just an exam. If you pass a vector, for instance, you can, if we pass a vector into your function and you need to use those values in there, make sure that you use the proper type of variable here. So if we're passing in a vector of ints, then you need to use an int variable on it, or a container of ints to take those things from that. So just stay consistent with what you've been given. That's great. Even if you feel like you want to use size t's or uint32s or whatever, use what's consistent with it when you don't have a choice, and when you do have a choice, use what makes sense. All right, that is the structure. Now let's talk about the success. This is the part that I love. We'll talk about how we're really going to win on this exam. For starters, you have to be calm. One of the things that is least helpful when you're going into an exam is worry. It never scores any points. You have to be calm. You have to take a deep breath beforehand. You have to make sure that you keep yourself from getting too excited or too worried or too scared. Put those thoughts away, and all we're doing today is scoring points. In many cases, this involves getting a proper physical routine before an exam. Make sure that you're well rested, but not groggy. Make sure that you've had enough food, you're not hungry. Make sure that you've got enough energy, but you're not jittery from over-caffeination. Figure out what your best physical routine is. A lot of times people like to eat bananas. That's a good one. They got great electrolytes in there, and potassium helps with the recall. Eat a banana half an hour before this. Figure out what your best physical routine is for an exam. That might take a few more exams, obviously. If you haven't figured it out by now, figuring it out by tomorrow isn't going to work. But as you work your way through the rest of school, figure out what really sets you up to be successful for an exam physically. Now you can even figure out what you're wearing, where you're going to be in the house, how you're going to do this. Make sure that you're in good shape. The next bullet, imposter syndrome. This is a course for you. You've been here all along, and you should be. We wouldn't let you in if you shouldn't be here, and since you're here now, that means that you can do it. Imposter syndrome is another way to let your mind drag you down. If you're worried about what you can't do or why you shouldn't be here, that's not helpful. That's something that you might want to consider later, but not during the exam. All of those thoughts out of your mind. We trust that you should be here. We trust that you can do well on this exam, so we hope you do too. Don't worry about it. You're gonna do well because you've worked hard already so far. And either way, win, lose, or draw, this thing is gonna be over in 140 minutes. So make sure that you put that calm in there too. The more relaxed you are, the more efficient and effective you're gonna be on this exam. The next one here is what I call being professional. You're professional students. I'm sure you've heard that in the past now. When you're going to primary school, that's not an option. You gotta go. You're in college now, university. What you're doing is optional. You've chosen this step to move yourself down the line, and that means it's time to treat this like a professional does. Take somebody that you know as a professional and look at how they behave. I take a couple of examples on a regular basis. I'm a musician, an ex-athlete. So let's start there. How do musicians that are professional work? They spend plenty of time practicing. They know when they go to a recital, they've got everything ready to go. They know everything and they feel supremely confident. There may be some jitters, but you jump up on stage and you make it happen. Same thing goes for athletes. You practice all week. You get your game plan. Gamers, you gotta have a plan. You get your game plan together and then you go execute it, right? Many football teams will have a scripted 10 plays. They start that game and they run those 10 plays no matter what, because they practiced all week. This play, then this play, then this play, then this play. Put that in your mind and think of, this is how professionals do the things that they do. You're a professional student. You are, whether you like it or not, a professional exam taker. So it's time to take an exam like a professional. I talked about having a plan. This is one thing that could be very, very, very helpful. One thing that is probably the utmost important thing for you to do is to read this exam from start to finish. That's the first thing you should do. Read the entire exam. There's a few reasons why you want to do this. They're very important, and this is one of the things that I can't stress more than I should. Read the exam. Once it's read, you've got your best asset on full court press there. That's your brain. Your brain can only work on the things that it knows about. So if you read the exam one question at a time, you only know one thing at a time. And you start adding more and more backload. Well, did I do right on that question? Did I do right on those 2 questions before this? Did I do right on these 3 questions before this? So all you've got is backload here. What reading before does is it opens up your mind to work on the entire exam all at once. It might sound a little difficult, but your subconscious will do it for you. When I was in college, I realized that my mind was working at all times. I would wake up and have answers. And so then I started going to sleep with a pencil, paper, and a calculator right next to my head. And very often I would roll over in the middle of the night, finally having figured out what my problem was, scratch it down on paper, maybe plug it on the calculator to make sure it works. Yeah, that's good. And turn around and go right back to sleep because my mind was at work, even though my body was asleep. So set yourself up here for success that same way. Read the entire exam. That puts your brain to work on it. Even if you're only focusing consciously on one problem, your subconscious is working on the other 25. Another thing that reading the exam ahead of time does is it takes care of this oh factor, or the oh no factor for our censored versions of it. But when you read a new problem, you're like, oh, am I ready to do this problem? Oh, am I ready to do this problem? And so if you work on one problem and then you work on the next problem and you work on the next problem, and that's the first time you've seen any of those problems, it's like a wake up call, and then you do a problem, then another wake up call, and then it's like wake up call. It's like somebody just keeps kicking the back of my chair. Every couple of minutes I get another kick in the back of my chair. Whereas if you read this exam from front to back, you're gonna know everything that's on it. That's it. It's gonna get those 26 scary bumps. It's gonna get them all taken care of all at once, which what that does is it puts your mind at ease and you go back to calm again. And the calmer you can get, the more efficient and effective you can be. So you read the whole thing, you get those 26 oh shits out of the way, and now you can just work on the exam very calmly. You might not know any more than before, but maybe sometimes you'll pick up something. And in any case, you won't be worried about, I'm going to turn to the next question. Is that going to scare me? Am I going to look at something I don't know? If you already know ahead of time what I do know or what I don't know, then it's going to be easier to get to it. I promise you. And then the last thing that's really important, probably the most important about reading ahead of time, is turning this into how professionals behave. And one thing that is great to watch in basketball games and football games alike is what happens at halftime. You see a team go in, having been dominated in a half, a coach gets a chance to talk to them. We had a game plan coming into this week. It didn't work. Let's adjust and do this. Regroup and get yourself together and now attack this, defend that, and they do better in the second half. Well, if you read the exam ahead of time, you can be the coach. You are the coach. You're the only person on your professional exam taking team. So you can say, well, I think that's going to work. I think this is what I thought was going to work while I was studying, but now that it's time to take the exam, I don't know if that's going to work. So come up with some game plans. Said you got to have a plan. Write some plans down. Here's some examples. I apologize here. I added 2 slides at the last minute. This is one of them. All it has is some game plans. And so what you can do is think about how this exam might go. Say, well, I know that the structure of the exam tells me there's 26 questions, 24 multiple choices, 2 free response questions. how might I budget my time in a way that most maximizes my ability to score points? So start up, first of all, we already covered this. Read the entire exam. That should take 5 minutes, maybe 10 minutes, somewhere in there, but it's going to be helpful. Even though I know it's going to feel terrible, you feel like, oh, I saw that question, I know the answer, let's do this one right now. Don't get stuck. Don't get stuck. Read it, then go back and do it. If you read it and you know it, you'll still be able to go back and do it. You want to get those points on the board, but I also want your brain working in the background. That's really going to help you. So read the entire exam, 5 to 10 minutes. Then on your cheat sheet, you should have some game plans. Here's just an example. Plans A, B, and C. Sorry, I'm drying up here. Plan A. Maybe in this particular plan, it's kind of a balanced approach. I'm going to spend 2 minutes on each of my 24 multiple choice questions. Then I'm going to spend 30 minutes on the free response 1, 30 minutes on free response 2. Then I'm going to take 1 more minute to go back and work on up to 12 of the multiple choice questions that maybe I had a problem with. So in this case, while I'm working on the 24 of them for 2 minutes each, if I get past that 2 minutes section, I just move on from that question, come back to it later. This version has an additional 10 minutes at the end where I can sort of spread them out on something that I might feel like later needs it. Plan B is 20 minutes on the free response question 1. Let's start out with the free response questions first. I feel like I might have more of a challenge on the free response questions, so I want to work on them as early as possible. 20 on free response 1, 20 on free response 2. Now I'm just going to hit these multiple choice questions once. So I'll spend 3 minutes on each of them. Once I'm done, I'm done. After that, I've got 6 minutes left to put on free response 1. I got 12 more minutes to put on free response 2, and the exam's over. Plan C, I really want to get some points out of these free response questions. So I'm going to sort of shade away from the multiple choice questions. I've always done well on multiple choice questions. This is my plan. I'll spend 90 seconds, minute and a half each, on the easiest 12 multiple choice questions. Just put those down. That gives me a half an hour to work on free response 1, 45 minutes to work on free response 2, because that's 24 points. That one question is worth 10 multiple choice questions. Budget, score, win. That leaves me now 2.5 minutes to work on those 12 hard multiple choice questions, and an additional 12 minutes at the whole end that I can just sort of spread around to fix whatever I needed to fix. And this leaves me time at the end to recap and review for 0 to 5 minutes somewhere. So these are some examples. This is what I'm saying professionals do, though. Professionals come into this with a plan, or 2 plans, or 3 plans. And here is like your halftime pep talk. You read that exam and you say, well, wow, I think that first free response question looks really easy. I mean, I already know how to do it. I bet I can get that done in 8 or 9 minutes. Great. Pick a plan that approaches that. Says, we'll take the one here, I'll move the one that has the least amount of time on free response question 1 and adjust that and put the extra minutes somewhere else. Do that, literally write it down on your cheat sheet. You should have your cheat sheet and be able to look at it, look at your clock, look at your cheat sheet and say, well, I should be working on this right now. This is 17 minutes into the exam. I should be on question 4 or a question 10 or whatever I've budgeted for. If you're sitting there trying to figure out what to do, guess what you're not doing? You're not scoring. You're not putting points on the board. You're leaving points on the floor. So make a plan or 2 or 3, and then if you read ahead of time, you can get yourself into one of these that's going to be most effective for you. All right? You got to have a plan. Last but not least here, take notes. Sounds a little ridiculous. Take notes during the exam. What questions do I have to work on still? Have I done well on this? If I spend 2 minutes on a multiple choice question and I've been able to take away 2 of the distractors, I know these are not the right answer. Write that down, so when you come back to this one with just 75 seconds to work on it again, you don't have to remember, oh yeah, I crossed that out. Oh yeah, I crossed that out. Write it down on a piece of paper. When you come back to it, it's going to make you go faster. Going faster scores more points. Because scoring points is all that we want you to do. We want you to score well on this exam. We know that you can. You will if you do well at it. There's a Canvas pro tip there. If you look up in the question header as you're on these questions, you can flag a question. This lets you see a question that you have to go back and revisit. So you can use that to flag the question and just move on. So check for that. If you haven't seen that in the past, go review one of your lab quizzes and see how that is easy to be done. All right, there is the pep talk. Now let's talk about the content. This is just going to be talking about what's on the exam. We've got complexity analysis. Of course, you've seen this slide before. This is just a big picture of how all of these things lay together. You should know this stuff. At this point, you should have a much better intrinsic feel. Maybe if you didn't have a great one before the semester did, you should have a great one by now. We've got our big O1, our constant time, that's the fastest, followed by our logarithmic time, linear time, log linear or linear rhythmic time, that's n log n. Then we get up into our higher level complexities there. We've got like n squared or other higher level polynomials, and then we get into exponential, and after that factorial and the like. So this is complexity analysis. That's going to be on there. Here's two pieces of code. What's the complexity of those two pieces of code? By now, we should know that we can always step count, although I don't really suggest step counting on the exam. You should be good enough now to look for patterns. Say, oh, I see a loop. That's a pattern that I'm looking for. I can look inside that loop very quickly and see there's a constant amount of work done inside the loop. So now I know only the number of times the loop runs is going to contribute to my overall complexity. So here I've got, in the first 9 lines, I've got something that looks like a binary search, what with the name being B search and all. But I've got a while loop. That's what's important. And what controls that while loop? As long as high is greater than or equal to low. I just look inside and see how high and low are modified. I see that I've calculated this mid as well as the high-low, and then I either adjust low towards mid or I adjust high towards mid, and I keep going. So this is something that looks like, because I'm calculating this mid by dividing by 2 there in line 3, this is going to be something that looks like it's logarithmic. I'm cutting the range in half. Anytime you're cutting the range in half or multiplying the iterator by 2 or greater, you're looking at something that's logarithmic. If I'm plus-plussing or minus-minusing, that's normally a linear loop. This is a logarithmic loop. So I can see that this is logarithmic there. In the second piece of code there, lines 10 through 19, I've got a for loop wrapping a for loop. Both of those are plus for loops. I is equal to 0, I less than size plus plus. J is equal to 0, J is less than size plus plus. Those are linear loops, linear in size, where n is equal to size. So since one is wrapped inside the other, I can think of that one pretty easily as big O of n squared. So that's the kind of thing that you should be able to do fairly well to do this exam right. How about recurrence relations? This is a recursive function, merge sort, line 1, calls merge sort in lines 5 and 6. So there's recursion for you. The question is then, how do I write the recurrence relation? As I look at this, I'm looking at some t of n, the time it takes to calculate the answer when my input size is n. Now I need to figure out, when I make that one call, how does it make more calls? In this case, it makes 2 calls to merge sort, and each one of those calls is about half the size of the data before. We see we calculate a mid again in here. That mid is used to adjust the ranges on those 2 merge sorts. So my t of n now is in terms of 2 copies of t times t of n over 2. There's another function in there, merge, which I would have to know something about. Of course you do. If this was a test question, we would say what the complexity of merge is, and this merge is a linear function. The rest of it, however, lines 2, 3, and 4, that's all a constant amount of work. So in terms of figuring out the complexity of this, I can completely ignore 2, 3, and 4. I look at 5 and 6 as both contributing a t of n over 2, and then 7, if I'm given some information about that, in this case, I think this is going to contribute an n. And so I end up with the recurrence relation looking like this. 2 times t of n over 2 plus some big theta of n. That's the merge, which takes some linear amount of time. I can use the master theorem on something like this. If I were going to do that, this is a perfectly good time to consult my cheat sheet and get some simplification on this. I know that the master theorem that we use in 281 has this a leading coefficient, my b denominator, and then my c largest power of the polynomial function of the work that's done within each layer of the recursion. So in this case, I'm going to look at how a, b, and c relate to each other, specifically how a compares to b to the c. So if a is greater than b to the c, what does that tell me? That tells me that my first term is going to be the one that's going to dominate. If a is less than b to the c, that tells me that my second term is going to be the one that dominates, the polynomial portion. So you see there, if you look closely at that, when a is larger than b to the c, that means that the recursive portion dominates. That's the t of n over b. That's going to dominate. When a is less than b to the c, that means the polynomial section dominates. And so this is an easy way to think of what those answers are going to look like. Then it gets a little bit more complicated when they're equal, and this is why the master theorem is great, because we don't have to figure it out. We plug in some values, click, 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 and then we get our answer out. So in that example that we used, we should be able to see that a is equal to 2, b is equal to 2, and my linear merge sets c equal to 1. So I've got a2, b2, c1. 2 is equal to 2 to the 1. So I'm looking at that middle case there. I'm looking for something like n log n. All right, here's another great test prep question. This is a terrible test question, but it's a good test prep question, and there's a difference. This test prep question has some really squishy answers in it. Like, I don't know, you could kind of lean this way and kind of lean that way. And that's good, because if you've got something that's a little ambiguous while you're testing, while you're prepping for a test, you say, well, it's ambiguous because it's unclear. If it was more clear, I could decide if it was this or that. I can give a good reason why. If you clarified it this way, this is the answer. If you clarified it that way, that is the answer. That's a great test question. We're not going to ask, I'm sorry, a great study question. A great test prep question can be a little ambiguous. So this one says we're looking for the best container given some conditions. Our options for the answers here could be singly linked, doubly linked, or vector. And then as an added bonus, the question is why? Why did you pick the one that you picked? Like I said, this is a great review question, not a good test question. First question, what is the best container if it will be used primarily to locate objects within it using a binary search? All right, so binary search, I look at singly linked list, that's going to be pretty much terrible because I can't get anywhere in the middle very easily. Doubly linked list is equally bad for that, so I'm going to go right away with this first question as vector. That sounds great. Best container if I'm going to be using a binary search, because I can get random access that lets me jump to the midpoint, jump to another midpoint, and constant time jump to another midpoint. So the first one I'm going to go with vector. What is the best container if new objects will often be added immediately before specific existing objects? All right. So if I've got a specific existing object, that means I'm already focused on an existing object. So if I've got access to that thing, I want to put something before it, and I'm going to be doing that often, I know that inserting things into a vector, even if I know where I'm going to insert them, still costs me a linear amount of time in the worst case. Whereas if I put them into a linked list, I can do that with a minimal amount of pointer manipulations. I can get that insertion done generally in a constant time if I've got access to the right nodes. And since I'm getting this specific object and I want to insert something immediately before it, this kind of is pushing me towards having this doubly linked list because I want to be able to look previous here. So this is kind of my thought process on answering a question like this. That's how I've pulled it all together. So I'm going to go with doubly linked list for that second one. And then the third one. Well, what do we got here? We got some things working in our favor. For starters, look at all that text. Just looking at the slide there, you can see there's 2 lines for the first bullet, there's 2 lines for the second bullet, and there's 4 lines for the third bullet. This exposes an exam truth. It's very hard to write a good exam question because exam questions have to be clear. They have to have enough information so that the tested person knows what's being asked, but not so much information as to give away the answer. That's why it's hard to write good questions. I feel your pity. Don't worry. So this one's got 4 lines of text here, so there's a lot of information in that question. You have to take all of it that you can. Try to figure out what's going on there. What is the best container if you must store a small number of very large objects? That's about where the last ones were ending. So what can we take from that? We got a small number of objects, not too many, and they're very large. Okay, goes further to say memory is scarce, and the most important consideration is to store as many of these objects as possible in the available space. All right, memory is scarce. Most important consideration is to store as many of these objects as possible. This one, is, like I said, is a little squishy. You say, well, I could pretty easily think that a vector has less overhead than a connected container because the vector is contiguous. So I could make an argument for this one being vector. On the other hand, I know that there was 3 questions and 3 options, so I might be shading towards, well, already used 2 of those options on the first 2 questions. Maybe it's the third one on the third question. So there's also good reason to say, well, a singly linked list here would be better than a doubly linked list because it uses fewer pointers, less overhead. So that is where you can come up with this one and say, I'm going to go with singly linked list. It allows me to not have to move these objects in memory, which could become problematical if they're very large objects and I can't put very many of them in memory. If I need to do some sort of manipulation, I might not be able to move them very well. So putting them in a vector might cause me problems. So, like I said, not a great test question, but a good review question because I just gave you some good reasons why it could be answer A, the singly linked list, or some good reasons why it would be answer C, the vector. And being able to enunciate that, being able to distinguish why one would be better than the other in the case of an ambiguous question is very important for test taking skills because then you're really getting to fundamental understanding of this stuff and not just turning around and grinding out some expected value. Let's try it again. 3 questions, same 3 options. Now we've gone from the best to the worst. So this is a different style of question. Find things that match was the first one. Find things that don't match is the second one here. What is the worst container if you must store a large number of 1-byte items and memory is the scarcest resource? Large number, small items, memory scarce. All right, if I've got a 1-byte item and I put a pointer up next to it, I can see that a pointer is 8 bytes. So if I've got 1 byte of data and then 8 bytes of overhead for pointers on that 1 byte of data, that's not really going to be helping me because I've got this very scarce memory resource here. So just having a singly linked list is going to take up 8/9 of my memory in overhead. If I had a doubly linked list, it's 16/17 of my memory is in overhead. So yeah, the worst one of these is going to be the doubly linked list. What is the worst container if you'll frequently insert new items anywhere within the structure? Oh, we know that insertion in these singly linked and doubly linked lists depends on where I get my pointers, but the actual work is actually done in constant time if I've got the pointers there. So you could say if I don't know exactly where I'm going, I would have to spend a linear amount of time with a singly linked list to get there and then a constant amount of time to do the insertion. or I could do a constant amount of time to get there with a vector, linear in a search, and then linear to do the insertion. So both of those seem bad. The doubly linked list, of course, would probably be the best. So I could see answering this one as vector or possibly singly linked list. Last one, what is the worst container if you will frequently insert new items at the beginning of the structure? Very clearly, I'm happy to insert at the beginning of linked lists, singly or doubly linked. I can get that done really quickly. So the worst container is anything that's not the singly linked or the doubly linked list. So that's vector again. So here we have a situation where we had 3 options, 3 questions, and we only used 2 options. So don't get tricked. Go with what you feel really discovers it. Sometimes you can use the structure of a problem to help you. Sometimes you can't count on that. Excuse me. All right, stacks and queues. Here's a good little thought question. This is a problem solver. Implement a queue using 2 stacks. Given the class below, write the pop function. So part of this is already done for you. You've got some code here, and you've got to use what's given to you. You've got some style to follow. Following style isn't always required, but it's usually pretty helpful. If you understand what's going on in the style and the overall intent, you can usually do pretty well with it. So this is class myQ. It's got 2 private member variables that hold stacks of ints, S1 and S2. It's got 3 public functions that we know of. The first one is given to us, this void push. And in that case, we take an integer and we just push that onto stack 1. That's what the push function does. Your goal here is to write the pop function. And there's also a front function there, which we don't have to implement. How is pop going to work? Take a minute or 2, I'm going to take a drink, and see if you can't put some code down and answer this question. Think about some concerns. Another thing that's helpful to do after you've written your version of it, think about the complexity of what you wrote. How does that affect things? We don't have a budget here, which is why this isn't a good exam question, but it is a good practice question. All right, here is 60 seconds to try to get this done. Go for it. Okay, we're going for it here. I have to write pop, and I'm trying to implement a queue. So what I'm going for is first in, first out behavior. So the first thing that I put in, I want that to come out first. But what I have is last in, first out storage. So the things are going to come out of my containers in reverse order. That's bad. It's not fitting my interface. But I got 2 of these containers, and it looks like I can take the one stack and take all of the things out of it and put them in the other stack, because I know that anytime I put things into a stack and then remove them, they come out in reverse order. So I put them in and I reverse them into the first stack, and then I reverse them into the second stack and pull them out. It behaves like a queue. There is the overall problem-solving aspect of this problem. What's left now is only the coding. Here's one example of how it might look, my pop function. And it says, down there at the bottom, line 18, let's go right there. Pop off of S2. So if I'm going back over this, I'll see that anytime they used push, things were put into stack 1. And anytime I use pop, something is removed from stack 2. There's an if clause above that, but that S2 pop always happens. S1 push in push always happened. S2 pop always happens in pop. So then nobody ever pushes anything from the outside into S2. The only way that I'll be able to pop something from S2 is if I put things into S2, and that's what this if does. When someone goes to pop, if S2 is empty, since we have to pop from S2, what we're going to do is take everything from S1, it's now in reverse order, pop it out of S1 and push it into S2. And that's what we see there in line 14, S2 push S1 top. That takes the top thing off of the stack, number 1, pushes it to as near to the bottom of stack 2 as it can, and then it removes it from stack 1 by doing an S1 pop. So this then reverses my reversed data and pulls it out. What did we see here in terms of complexity? Any idea? It looks like I always do S2 pop, so I can get that done in a constant amount of time. So in terms of line 18, that's a constant amount of work. But then sometimes this 12 through 17 looks like it could take me a linear amount of work. It takes everything that's already in the container and moves it over. So sometimes pop is very fast. Sometimes the same function pop is not so fast. This is a perfect case for amortized complexity, because I can tell that no matter how many items I have, if they all get pushed into S1 and they all have to be popped out of S2, that they'll all have to be moved over at some point or another. Maybe it's push 1, push it again, pop it out, or push 3, reverse them and pop them out. But every item is going to go all the way across, all the way back, and then all the way out. And if that happens for all n of those items, I can say that this looks like it's amortized constant. If you haven't figured that out or still don't get that very clearly, you should definitely talk to somebody today in office hours. But this is an amortized constant because we do the same amount of work for every item. We just don't do it all at the same time. If you think about this, every item gets pushed into one container, it gets popped from that container and pushed into the other container, and then it gets popped out of that container and removed. So there's the same amount of work for every item. Sometimes they happen in different order because we've pushed 3 at a time and then pushed 3 at a time over here. But in the end, everybody gets pushed, pushed, popped, popped, and they're done. So this is amortized constant. And for those of you who haven't had this one completely figured out, no, we don't have to put things back from S2 into S1 to support more pushes. If you want to think about how this might work, let's push 1, 2, 3, 4, 5 over here into stack 1. Now, when I'm ready to remove those items, what I want to do is I'm going to pop them over into stack 2. So if I put 1, 2, 3, 4, 5, and I push them over into stack 2, now I've got 5 at the bottom, 4, 3, 2, 1, and the first thing that comes off is 1, and I'm happy with that. Now if someone wants to push 6, where does it go? It goes into S1, and that's okay. Remember, I only move things from S1 to S2 if S2 is empty. So as I continue to add new things, they continue to pile up on stack 1, even as there's things in stack 2. And once I remove everything from stack 2, I can invert stack 1 again back into stack 2, and then you'll see that the 6 is the first thing to come out after my first 5. So if that's not clear, you should try writing this one up. How about sorting? We talked about this in the past. Sort, by default, means ascending or increasing sort, things that go from small to large. So unless it's otherwise stated, you're always going to be using an increasing sort. We're always going to be using the best, most adaptive versions of the sorts that we've developed. So if we're talking about how does an insertion sort work, we would be using the one from our adaptive version in the slides. So a lot of times we'll ask the question, which one of these sorts is the best given these circumstances? What happens if an array is almost already sorted? Which one of those sorts is best? What if I've got a very small array? What if I've got a medium-sized array? So now we're already looking at some bad test questions. What is a very small array? What is a medium-sized array? I don't know. But as you think about what makes it small or what makes it medium-sized or what concerns are raised when it goes above a particular size or below a particular size, that's good test prep. So if I've got a large array, about as big as main memory, now that's telling me something that I don't have enough room to do an extra copy of things. That might rule out a particular sort. How about a very large tape drive? Now, this one is pointing us towards merge sort, hopefully. We know how merge sort was originally a tape sorting algorithm in the first place. Then there's a question here at the bottom. You're using a quicksort on a very large input, and it's taking longer than normal. What happened? So this is 6 questions. Let's get those covered. An array that is almost already sorted works really well with insertion sort, or maybe bubble sort. We know that we fix a few things when there are a limited number of inversions for every item. Then insertion sort and bubble sort work like they're going to happen in linear time. For a very small array, we know that insertion sort is what the STL uses for small data. So insertion sort works there. Selection sort might be used. Remember that selection sort is not our favorite sort. It's the one that doesn't go so fast. But since it only does a fixed number of moves, that linear number of moves, if I got really large data and have expensive writes, then I'm okay with actually even doing a selection sort here. So this is a good depends answer. This one, it depends on what I'm looking at data-wise. How about a medium-sized array? Quicksort, probably the best. We like quicksort when we can use quicksort, maybe heap sort. In a large array, this one is about as big as main memory. Here, I can use heap sort to get that done in place. I can't use merge sort to get it done in place. I may not be able to do quick sort. A quick sort might have too many levels of depth, right? I've got a very large array, so there's a chance that I could go fairly deep. And if I've already used up most of my memory here, then I don't have a whole lot of extra heap space to go very deep. So my large array here is going to push me toward heap sort, or maybe an in-place unstable quick sort. We haven't really talked about that, so don't get too bogged down on that one. Heap sort here is going to be my best answer. A very large tape drive, of course, merge sort. And the last question on there, you're using a quick sort on a very large input and it's taking longer than normal. What happened? I repeatedly chose a bad pivot. And the more often I do that, the more I'm going to approach a big theta of n squared. We talked about binary heaps, so be ready to answer questions on binary heaps. Here's an example question. Draw the underlying array for this heap. So we remember how to write these. Well, this tree is this very complete binary tree here. So I've got everything from top to bottom filled, then left to right where it's empty. So I can put all of this in an array and use my integer index math to figure out parents and children here. So this is an example. Draw the underlying array for this heap. Talking about how it's done physically. We see the picture here is how it's done logically. Then try pushing the value 47. Use fix up. Draw the resulting tree and array. Think about how that might be turned into a test question. Hey, what happens when I push 47? What is the left child of 18? Is it 9? Is it 7? Is it 2? Is it 14? That's a perfectly good multiple choice question. And if you don't understand how to do a push and fix up, then you can't answer that question. So there's a perfectly good way to go at this. I could say, well, here's some options of binary heaps. Which one is the correct one? That might be a multiple choice question. So when you get topics here, try to figure out, how can I write an exam question for that? So in this case, here's what my physical version looks like here on the right, this array, my logical version, the tree on the left. You see that in my binary heap physical version, I've got this array that holds 81, 18, 14, 9, 7, 1, 5, 2, and 4. So that's the heap that is similar to the original tree with 81 at the root, left and right children, 18 and 14. 18 has left child 9 and right child 7, with the 9 having a 2 and 4 as its children, and the 14 has a 1 and 5 as its children. That is a binary heap physically and logically. When I go to push 47, I know that it's going to go into that index 10 in this one-based indexing scheme. And as I fix that thing up, it's going to supplant things all along the way. It's going to move the 7 down, it's going to move the 18 down, it's going to move the 8, and then it's going to stop there because it doesn't move the 81 down. Excuse me. All right, priority queues. Here's some questions that hopefully you feel really comfortable with after the part 2B. We had to write an unordered array version. We gave you an unordered array version. And then you had to write an ordered array version. You also wrote a binary heap version. So you should understand what it takes to calculate these in range, or to create them in range, and also what the 3 primary operations, push, pop, and top, all cost. In our unordered array, I can just throw all of that stuff in there however I get it. If I've got a range in them, I just copy them. I can do that in linear time. To push, I can do that in constant time or amortized constant. I just stick it on the back. If I need to go allocate more space, I move over and do that. That's where the amortized constant comes from. Top, however, in unordered is more difficult because I have to find the most important item, which, since it's unordered, requires a linear search. So I do that linear search, and then pop. Once I know where the item is, I can get that out in constant time if I swap it into a good position. So I would say that the first column there is linear time for unordered array creation. Push is in constant time. Top is done in linear time. Pop is either linear or constant, depending on whether or not you did a top before that. In the sorted array, the creation requires me sorting all of my data, or inserting each one of those things into a sorted container, which is going to be n log n. The push, of course, I can binary search to figure out where the item goes, and then do a linear insertion. So a push is linear. Top, since I know the most important item is always at the back, I can find that in constant time. I can pop it in constant time because it's at the back. In the binary heap, we can create that in linear time with heapify. That's, remember, our bottom up, fixed down repeatedly. I can push now in logarithmic time. I can pop in logarithmic time because I have to break it and fix it again. And since my item is at the top of the heap, I can always get that in constant time. Here then is what that looks like in terms of our answer slide, and each one of those values should make a whole lot of sense to you after P2. Strings and sequences here. Probably the most important thing that we talked about in that lecture was understanding how to use fingerprints. A little bit about how they're calculated is important, but not really at the testing level. We won't have you calculate a string fingerprint. In any case, we would give you a simple function to say, well, maybe the fingerprint is the ASCII code of the first character, something like that. Something very simple. So you wouldn't be calculating string fingerprints, you would be using string fingerprints. So understand why that works. What does it tell you if two strings have the same fingerprint? What do I know about them? If they've got the same fingerprint, do I know that they're the same? They might not be the same. If you don't understand why that is, it's a good thing to figure out. It has to do with that modular arithmetic. As I keep adding these things and taking this modulus, right, I could get two values that are different that have a similar or the same fingerprint. So that's why I can say that if I know two strings have the same fingerprint, they might or might not be the same string. But if they are different fingerprints, then I'm definitely convinced that they are different strings. That just about covers it. Remember the important things. Number one, stay calm. Number two, you got this. Number three, it's going to be over soon, and then we can move on. All right, I have faith in you. Let's talk some more today and get this done tomorrow. Take care.